Hello, welcome to today's session. So, I was thinking we could have a doubt clearing session for linear regression because on Saturday's session there was a session on this decision tree classifier and regressor. So, we can have some doubt clearing session related to linear regression, or even if you want to discuss about decision trees, you can do that. So you can just raise your hand and ask your questions. You can type your questions in the chat also if you don't want to ask. Anyone? Okay, so Saurabh is asking how much content of this course is helpful in order to get a job. Is it sufficient or do we need to do a few more extra things? Okay, so Saurabh, the course it covers the basics of machine learning, which is required for you to know. So other than this, I think you should also try to start some projects on your own. Of course, this course will help in understanding the basics, but you should also try to do some projects, or you can join some competitions on Kaggle to get more experience in the application of these algorithms. But yeah, you have to finish this course first because you have to know the basics to know how to approach your problems. What do you mean by a brief on machine learning? I mean, it is a big topic, so can you be clear what you want to know? Okay, so I think this course covers all of the basic algorithms. You need to know what is linear regression. You need to know about decision trees because these are also useful in the real world problems. And you also need to know nearest neighbors, support vector machines, and all these topics will be covered in the course. So yeah, these will be covered in the coming lectures. So yeah, you should go through them. Okay, Bhushan is asking me how to use decision trees for linear regression. Okay, let me share my screen. . 。 . 。  . 。 . 。 . 。 . 。 . . . . . . 。 . 。 . . . 。 . . . . 。 . . 。 . 。 。 . 。 . 。 。 . 。 。 . 。 . 。 . 。 . 。 .
。
Okay, so you have seen how, so suppose you are given some data set T, you, on the basis of the values of your attributes, you partition those the data set into, say, D1, D2, and so on. At last you get to some leaf node, right? So suppose these are your leaf nodes. So suppose your data or the labels of your data are continuous. Suppose it is suppose it predicts the cost of the house given your area of the house, location of the house. So at first what you will do, suppose uh, you will check what is the area of your house. If it is greater than some values, then you will go to this node. If it is less than some value, you will go to this node. And similarly, then you will go to some other decision, maybe it is the location of your house. So based on that, you will again have some different branching based on that. So at the end, what you will get are some leaf nodes where, suppose you have some m data points here. So you will have some values, say y1 for the first data point, y2 for the second data point, and ym for the second mth data point. So what you will do is, given some test data point, so these are all continuous values. So these are regression values for those m data points. So given some test data point, suppose you arrive at this node. Suppose after going through all those decisions, we arrive at this node. So decision for the test data point will be an average of these data points. So this will be the regression value for your test data point. Is that clear, Hushan? So Shankari is asking, can you solve one problem in MSc calculation in linear regression? Uh, One problem means, okay, I will show you an example of linear regression. So it has already been discussed in class. So suppose you have one feature, say x, and you have these points y, and suppose your your points are, say, like this. So now I learn a decision, or sorry, I learn a linear regression to fit to these points. Suppose this is the line, right? And suppose this line is your beta naught plus beta 1 of x. So so this was our point, say d1, so d2, d3, d4, and d5. And suppose this is your x1, this is your x2, x3, x4, and x5. So if this is your line, suppose this is, say, y tilde. So y, or sorry, this is your f that you are learning. Your f of x1 will lie on this line. So f of x1 will be, say, beta naught plus beta 1 x1. Your y of f of x2 will be beta naught plus beta 1 x2, and so on. But your d1 was this one, this point. This was a d1. So there is this, if you look closely, there is this difference in your calculation. So you are getting, your predictor is saying that this is the value and actual value was this. So this is the difference. So what we do is we say that the error for point 1 is d1 minus f of x1 whole square. Similarly for point 2 we say that the difference is d2 minus f of x2 whole square, and so on. We do this for all the 5 points. So overall our loss that we define is, since there are 5 points, I will say 1 by 5 I equal to 1 to 5 ei. So this is our loss function, and we want to minimize this loss function to learn these parameters beta naught and beta 1. Once you learn these parameters, the slope of this line, because we are changing the slope of this line and intercept, the slope will change based on what beta and betas are learned, and that will give us the optimal solution for this linear regression problem. Is that clear, Shankari?
Sir, how to find this beta 0 and beta 1?
How to find? Okay. So suppose, yeah. So let us look at the loss now. This is 1 by 5. Summation I equal to 1 to 5. Say d1 minus f of di minus f of xi. This is your point, right? So we can write this as 1 by 5 your di minus beta naught plus beta 1 xi. Since this is the line that you are since this is the form of the function that you are assuming. So what we do is we want to optimize it. So these are our unknown parameters. Here are unknown parameters of beta naught and beta 1, right? We want to learn beta naught and beta 1. So if you remember, now we have to minimize this loss, right? Because we want this this loss to be small. So our problem becomes minimize L with respect to beta naught and beta 1. So you must remember from your basic maths class that in order to minimize a function, what do? We differentiate that function with respect to the variable. So if L is minimum with respect to b naught, we know that the differentiation should be 0. The derivative at b naught should be 0. We also want to minimize it with respect to beta 1. So this should also be 0. So if we do this, if we minimize this loss with respect to beta naught and beta 1, we'll get some sort of equations. And once you solve those equations, we get solving these equations. Is that clear?
Okay, sir. Thank you.
Well, I think Nagamali is asking, yeah, this will be a doubt clearing session. Or if you want to discuss some problem, we can just discuss it here also. So it's up to you what you want to discuss. Question is asking why we use decision tree for regression when simple cost function we can just a linear regression. So that is because one advantage of decision tree is it is interpretable. So you may come upon this term interpretable. So what I mean by interpretable is at each point you can see why you are going to that direction, because we want to know why the machine is making certain decisions. So decision tree are very interpretable functions, and we want to, this gives us a good understanding of why we get the result that we get.
Sir, linear regression cannot be applied to classification, right, sir?
Linear regression, it cannot be directly applied to classification, but you can have do some tricks and then apply it to classification. So suppose your classes are say 0, 1, 2, 3. Suppose you have 4 classes, and suppose you are using a linear regression for this, and we want your regression values. So you will get some y1, y2, y3, y4, and we want this y1 to be close to 0, we want this y2 to be close to 1, y2 3 to be some close to 2, and so on. We can, this is not a straightforward task, we have to do some adjustment to the algorithm such that our regression is such that these values are predicted instead of the real classes. So instead of say 0, it may produce say 0. Y1 maybe say 0.00001, y2 maybe say 0.999. So because now you can see these are continuous values, right? So we can have a regression problem which tries to predict values as close to the classes that we want. So you can use regression for classification, but you have to do some modifications to the
We have to make some assumptions, right, sir? And then
assumptions. Yes, yes. You have to transform this to a real valued vector, and then you can apply it.
Okay.
Pardon, Dandas is asking, can we continue and solve the equations? Well, it is, yeah, I can solve it, but yeah, you just have to minimize this, right? So if we, with respect to beta naught, you will get some form like, okay, let me do that. So our L was, so we have to, so first you require this, you'll have this 2 that will come out. And then because we are differentiating with respect to beta, we will have something of this sort. So yeah, because beta naught is b1, so we'll have to solve this. I think we will get -1. If someone can help me out. So if you solve this equation, you can get some function in beta naught and beta 1. Similarly, you apply this to the second part. Then solving these two equations, you will get beta naught and beta 1. Is it clear? Pardon, Tanji.
Yes, sir, it's clear. Thank you.
Okay. So Prabhjot Singh is asking. Yeah, I think the certification exam will be MCQ based, but you should clear it with NPTEL.
Sir, there is one very basic doubt, sir.
Yes.
Whenever machine learning algorithm is explained, usually the professors, they start with training example. X comma Y is a training example.
Yes.
And they also tell X comma, sometimes they take X comma F of X is a training example. Here Y is nothing but Y is equal to F of X. That's all right.
No. So when we say that XY is a training example, so that means your X is known. So if this is a training example, your X is given and Y is also given. Right? Now you want to learn some F such that your F of X is close to Y. So if you want to learn some function such that applying that function on X, you get some value which is close to the known level. So this is your known level. This F of X is your computed. So based on what function you learn, this F of X is your computed label, and you want to learn some F that such that this is the case. So X, Y, and X of Fx those are two different pairs of points. Is it clear?
Yes, sir. Yes, sir. Thank you, sir.
So Gauri, I think you should mail the NPTEL team and ask about this, what they plan to do. So you must have gone through this. Let me show you. So is this screen visible to you?
Yes, sir.
So yeah. So this notebook has been given in the course website. So this has been prepared by a previous TA Anirban, previous TA for this course. So this has some nice problems that you can go through. You can download this from the given GitHub link. So let me show you a simple run of this linear regression. So for those that are not clear, so these models such as linear regression or decision trees are available in this sklearn data package. Okay, so that's why I will share the link. So I've shared the link in the data in the chat. So yeah, I was talking about this scikit-learn package. So whenever you want to run some well-known algorithms like this linear regression, logistic regression, decision tree, you go to this sklearn, and then you will find implementations of these algorithms. So here, suppose we want to see how linear regression works on some given data set. So we import this linear model module. We require some data sets to run our algorithms on, and this we import this tree for decision trees. So then we go to this matplotlib package. So like you can see, it is always good to visualize your data. So matplotlib it provides you some functions to plot your data, so you can make decisions on what type of algorithm you want to use. So suppose now we look at the linear regression. So suppose our linear regression points are uh, derived from using this function as given here. So the points will look something like this. So we have taken 100 points here, and it has one feature, which is this x. There are 100 such points, and these features are in this range from say minus pi to plus pi, and our y is generated. Okay. I think you can get this file in your this. So if you go to week 2 and you go to this Python exercise lecture 10, so there is this GitHub link that is given here. If you go to this GitHub link, you can see this file. Can you confirm if you are able to access it in this way? Okay.
Yes, sir.
Okay. So yeah, so your y or your labels are generated using these functions, x by 2 sin x plus this. So now we form this is called a scatter plot, because we want to see how our data is scattered, right? So we use this scatter function from pyplot, and we plot the x and y, and you can give your labels like these are the features and these are your target values. So now, as you have seen in the first week, you saw that we always divide our data into train, test, and validation, right? So that is what we are doing. We are doing a random shuffle of the data set. So we can use this permutation function for that. And since there are 100 points, we are taking 70 of these points for training. Similarly, we take your x and y are different factors. So we are taking the first 70 points from x and the first 70 points from y for training. Similarly, we take the remaining points for validation and testing. So now, how do you learn this linear model? So first of all, since you okay, Apeksha, these classes are held every week. So there is a session on Saturday, on Monday, and tomorrow there will be another session. So each week you will have 3 such sessions taken by 3 different TAs. So you can join in any one of them, and you can find the recordings in the course website. Okay. So we saw that we imported this linear model module earlier. So we form an object of this linear regression class. So this model is an object of this linear regression class. So now, since we want to fit our training examples to this linear model, we reshape this. So these reshape functions will try to shape your data in any way you want. So here we have some one-dimensional vectors whose length is given by this length of extent, and one is the number of columns that they have. So we apply this to train also. So when we want to train the data, that is the given by this fit function. So in any sklearn model, you will have always have this fit and predict function. So this fit function will learn this function f that we want for the given x and y values. So then we plot this function that we get. So here this function that we get is given by the predict function. So this blue line is a predict function that we learn, and these are the these black lines, black dots are the points that we had in the data set. So now we want to evaluate this model, how good is our model. So we want to see what is the distance of these points from this line. So that is given by this squared loss, mean squared error problem. So we plot what is the error on the validation set and what is the error on the test set. So you see on the validation set our error is around 3.69, and our test set is has an error of around 5.07. So this is the basic flow of our machine learning model. If you whenever you learn try to solve a machine learning problem, these are the steps that you have to do. So first you have to first visualize the data, because based on the spread of the data you have to decide what type of functions you want to learn, and after that you create test, training and validation sets, and then you call your fit and predict functions and evaluate that based on what type of loss you want to minimize. So this was a basic demo of this linear regression. Any doubts on this? So Himanshu is asking, how do you say it is a good model metric? So one thing is based on the validation set, you can say at what is, because you will have some idea of how much, suppose you are doing some classification and you want to say that I want a model that gives me 99% accuracy. So based on that, you will, once you compute this, once you learn your model and do the predictions, then you will get some. So here we are looking at MSE. For checking accuracy, there are other functions, and you can check what is the accuracy that it is giving. So this is up to the user actually, what model or what metric we want to use. Suppose we said we want a model whose test loss is less than 1. So then we'll use a more complicated model to fit to this data. Is it clear, Himanshu?
Hi, actually, I just wanted to know, like, how do we decide that? Like, we have some live data and we have performed a regression. We have got certain MSE for the. Am I audible?
Yes, yes, yes.
Okay, so we have got some MSE for the validation and test data. Now we are not able to decide, like, is it a worthy model? Like, is there some objective way, like, we can understand, like, this model is working good for us or not?
Okay. So actually for this linear regression type of model, you have some closed form solutions. So closed form solutions means that you have the exact minimizer. Yeah. So closed form solutions means you have the exact minimizer at that point. So for linear regression type of models, you can know that what is the minimum possible loss you want to get. So, but computing those closed form is computationally expensive because it involves some matrix vector operations. So what you do is, suppose somehow you are given that closed form solution, so then you go to this iterative solution or whatever type of solution you want, and try to compare your loss, your validation or test loss on the optimal loss that you have. So that is how you, so you want your model to be as close to the minimum as possible. Was that what you were asking? That is how you evaluate your model.
Yeah. Fine. I got it.
Okay.
Right. Thank you so much.
So this also has some other algorithms like logistic regression and uh, decision trees. So you can, I hope you can access this GitHub page, and then you can go to Colab. So there, Google has this Colab website, that's where you can run any of these Python or Jupyter notebooks online. You don't need to have any specific GPU on your system. You can just go to Drive, and then you can, so here I went to the Drive. I say open with Colab. So then there is a connect option here. You can connect, and then you can run your programs, and all these packages are already installed in Colab. So you can run these notebooks in Google Colab.
Sir, depending on the kind of data we have, we decide on some machine learning algorithm.
Yes.
But when we choose a machine learning algorithm, is it dependent on the developer to select the parameters and hyperparameters?
Okay, so those are two things. So when you say about parameters, so here, since we are talking about linear regression, so parameters are not unknown quantities, right? Here beta naught and beta 1 will be an unknown quantities. So these are your parameters. Suppose you are working on some, say, neural network. So there your parameters will be different. So based on the algorithm that you use, your set of parameters will be different. What type of function you want to learn, based on that you will have separate set of variables that you want to learn. No. Now when we talk about hyperparameters, suppose you must have seen this gradient descent algorithm that ma'am discussed in the course, right? So this gradient descent algorithm, so what it does is, you have some, this is your loss function, say, and you want to get, so here the loss is 0, or this is the not 0, this is the minimum loss, and you want, suppose suppose at this point your parameter values are b0 dash and b1 dash, and you are starting out at this point, and you want to come to this.
Sir, your screen is not visible, whatever you are writing.
Oh, okay, sorry. Yeah, so as I was saying, suppose you have this is your loss function, this is your loss surface, and you want to come to this minima point, because here your loss is minimum. And suppose at some point your parameters have values b0 dash and b1 dash, and you want to get to this point, say b0 optimum and b1 optimum. So how do you travel from say this point to this point? So for that case we use the gradient descent algorithm. So what it does is, at each step it will try to move up, it will try to move from this to this direction, right? So it will move. So you will, so from B0 dash and B1 dash, you will go to another point, say B0 tilde to B1 tilde. So for this, we will move on the loss function from this loss to this loss, because here the loss is a little bit less. So again, you will go from this point to this point, this point to this point, and eventually we will arrive at the minima. So this is what the gradient descent algorithm does. Now, if we look at the gradient descent algorithm, the update step is given as, so suppose we have some parameter B0 tilde. So this update step is given as B0 dash minus alpha times gradient. Suppose this is our loss, gradient of the loss, gradient of the loss. So these are, so your B0 dash is your current point where you are at. Gradient of the loss is the slope of this loss at this point, or negative of the slope of this loss at this point. So your gradient is in this direction, the negative of the slope is in this direction. And this alpha parameter, it controls how much you want to move. So you can move from here to here, or you can move from here to here. So if alpha is small, you will take small steps. If alpha is very large, you will take large steps. So this is one hyperparameter that is generally used in machine learning. So it controls how fast you get to the minima. There are reasons why you cannot take very large alpha, because suppose you take a very large alpha, so you will get to this point, and after this you will get to this point. So here you skip the minima, and your algorithm will not be able to find the minima. So that's why this alpha is a hyperparameter that is dependent on the type of loss that you, and this requires tuning, which is referred to as hyperparameter tuning. So this is the difference between parameters and hyperparameters.
Here, sir, hyperparameter is alpha, sir.
Yes, this is your hyperparameter, and your parameters are the ones that you are learning. These beta knots are the parameters.
Beta and beta 1 are the parameters, and alpha will be the hyperparameter.
Yes.
Sir, many times ma'am uses these words like global minima, local minima.
Yes.
That is all whatever you told. This is what, right,
Yes.
sir?
So these type of functions, so I'll get to that. Suppose you have these type of functions. So in this function, you can see that there's only one minimum point, right? So these type of functions are said to be convex functions. You don't need to go into details, I'm just mentioning. And here, wherever you go, this gradient descent, it always give you the global minima. This is the global minima. But there may be some loss function which is something like this, right? So what happens is, if you use some gradient descent algorithm, it will come to this point, and you see here your derivative is 0, right? So yeah, whenever you are at a minimum, your derivative is 0, like we saw here. So if your
Yes,
derivative is 0, your slope is 0, so the algorithm will think that it has reached a minima. But actually in this function, this was the global minima. But since you started off here, you are not able to come to this point, so this is a local minima. So these type of functions are said to be non-convex functions. So in neural networks, our loss functions, in deep learning, our loss functions look like this. That's why it is not able to get to the global minima. We always, most of the time, we get a local minima in this type of functions.
okay, sir. Understood, sir. Thank you.
Hello.
Yeah, hello.
Sir, in case of when we are getting several local minimas, then which solution should be considered the optimized solution, the optimum solution of that problem?
So suppose you are minimizing on this loss function, and suppose your, so like I said, you want to evaluate your model, you want your model to have the least possible loss, right? Suppose your model tries, once it get to this point, it will get stuck because it will think that this is the minima that it has obtained. But still you want your model to be bit more, it will, so you want your model to give us some better solution. So you want something like this. So this getting to this point is a hard problem because you need to have a good initial point. Suppose you initialize your function at this point, so then it will get to local your global minima. But suppose you come initialize at this point, it will be a hard to come to this local minima, global minima. It will always converge to this local minima. So whenever you are trying to learn a function, you always try to have a good initialization. So there are various schemes for that. And suppose you are not satisfied with this, you will try to, at this point you will try to increase the learning step. So suppose you increase the learning step and it comes at this point, so then it will come to this minima which is less than this. So if specifically talking about neural networks or stochastic gradient descent, you will get different loss function, but which is, it is very hard to find the global minima. So overall you want to find the minimum that is as less as possible. Is that?
Yes. Yes, you were saying something, sir.
No, yeah,
You
that's
were
fine.
adding. Okay.
Oh, is that clear?
Thank you, sir. Yes.
Sir, gradient descent, stochastic descent, these are all different ways, I mean different algorithms through which we can reach this minima, right, sir?
Actually gradient descent is the same algorithm, so their weights are updated uh, with this type of update rules. The difference with say batch gradient descent, so what you're asking is there are different versions of this gradient descent. One is this batch gradient descent, one is this stochastic gradient descent, and there are other varieties like mini batch and so on, right? So when we are talking about batch gradient descent, we look at the whole data, before taking a step. Say for this example, here we are talking about the loss, and this loss is a summation of all the points in the data set, right? Summation of all the points in the data set, and we are talking about loss with respect to the all the data points. So when I talk about stochastic gradient descent, instead of looking at complete data for creating this gradient, we look at only one data at each step. So what it does is, computing this loss is costly, right? Because if there are 10,000 points, you have to wait till you compute this loss for 10,000 points. But if you are doing stochastic gradient descent, we'll only look at the loss for a single point. Based on that, we'll take some step. So these different versions of batch and stochastic gradient descent are due to what amount of data that you are looking at. So batch gradient descent will look at the whole data, stochastic will look at only one point at each step, and mini batch will look at a small subset of the data. So this is between batch and stochastic gradient descent.
Okay, sir, understood. Thank you, sir.
This is Bhushan. Is stochastic gradient descent accurate because you're only looking at one data point at a time? I mean, how do you go about it? Is it really reliable?
Yeah, so stochastic, so this is a randomized algorithm. It is not guaranteed that you will get to the minima, but it has certain, because this is a randomized algorithm, you will have certain guarantees that you will. So suppose you are at uh, yeah, you are looking into this convex function. So at some point you will come to this point. So at next point, if you look at the gradient, maybe the gradient is increasing. So because you are doing this stochastically, overall, if you take the mean of your all of your results, it is expected that uh, uh, it follows the gradient of this loss function. So it is not guaranteed to give you global minima, but in expectation you'll get to a good local minima because of the stochastic gradient descent. Because when you are talking about gradient descent, this beta will be updated only once after you get to the data. But if you look at the stochastic gradient descent, it will be updated every time you look at a point. So say this will be updated about 1000 points, but here if you look at 1000 points, your bets will be up, your gradients, or sorry, your parameters will be updated up 1000 times. So you have some certain guarantees that this will lead to a loss function that is better, or that is better than the ones you get at full gradient.
Okay,
Is
thank
that
you.
clear?
Yeah, yeah. Now, one just a quick question, that is, given a set of data points, is it possible to determine whether it is going to have only a global minimum, or how do you find out whether it is also going to have a local minimum?
Oh, so your loss function does not depend on your data points. It depends on the type of function that you are learning. So in linear regression, we were learning functions, or your loss function one of was of this type, right? L was yi minus f of xi whole square. So these functions are convex functions, and it is guaranteed that it will have a global minima. But if you're looking at other type of functions, say neural networks, these are not such simple functions. So those are generally functions of this type. So based on the type of algorithm that you have, your loss surface or your loss function will be different. And based on that, you will have maybe one global minima, or you have multiple local.
Okay, thank you. Thank you.
Okay. So Jitendra is asking, hyperparameters are those which you said yes. Hyperparameters are given by the user. So based on which hyperparameter gives the least validation loss, you select that hyperparameter for testing.
Sir, only after finding all this local minima and I mean global minima, everything, that is when the new unseen data is given to us, we will be in a better position to get the result, right, sir?
No, it is not the case, because you can look at the unseen data anytime. So you will have some goal, right? We want our model to have, say, this much of loss. If you're talking about the regression, suppose I say that I want my model to have loss which is less than, say, 0.05. So once we train our model such that the loss goes less than 0.05, then you can go to a testing step. So it is not guaranteed whether when you get the loss at 0.05, you are at the global minima or local minima. So the global minima, it says that this is the, for the given function, this is the minimum possible loss you can get. So if you are lucky, if your initialization are good, your hyperparameters are good, you may get this point. But otherwise, finding this global minima is hard. So most this neural network type of algorithms, so they always try to say that this local minimum, because we say that our loss is at most 0.05, we are happy with this much of loss, and so we test the data on that parameters.
Okay, sir. I guess when it comes to the accuracy, then we can say that then I think these points will make a difference, right, sir?
Yes, so if you want 100% accuracy or zero loss, so maybe then you need to wait till your algorithm goes to the global minima. But in most of the cases, because we have seen that if you have zero training loss, that means your model is overfitting, and you don't want your model to overfit, because once it overfits, your test error will not be good. So that is why you do not want to go to global minimum in such cases. So it depends on the specific type of problem that we have.
Okay, sir.
In our lectures, we are also getting that Python lectures. What is the purpose of that? Are we in this course? Are we going to do any Python coding, and as a part of the exercise?
So yeah, you will not have Python coding as an assignment. So you may get some small snippets of code in your MCQ questions, and it may ask what will be output of this. But these Python exercises are actually so they give a demonstration of the algorithms using these notebooks that they have. So if you want, you can go to this GitHub link and download these files and run it yourself, or else they give a good explanation of why this code is working, and all those type of things.
How do you run it yourself? You said we have to download it from.
Okay, so here you can see there is this. Okay, let me share. So is it visible? Is this screen visible? I am showing the course website.
No, not visible. You are.
Okay, it is visible now, right?
Now it's visible.
Yeah. So if you go say this lecture 10, there is this link that says you have this link to GitHub, right?
Okay.
So it will take you to this GitHub page. So you download this file, you upload this file in your Google Drive, and then you go to this Open with Google Collaborator.
Okay.
So once you go there, you connect to the collab, and then yeah, let it connect. So once it connects, you can run your code. You can run this code, or you can test with different values of y on all those things. So those are for your own practice. These won't. There will be no coding assignments.
Okay. So we have to download this code, upload it into what is that? Google.
Drive. Yeah, upload it to Drive, and then you say open with Google Collaborator.
Okay. Uploading to Google Drive, there is some specific thing allocated for us. How do you upload it to the Drive?
You will have your own. You must have a Google account, right? So you will have an access, right?
Yeah, I have a Google account.
Yeah,
my own personal Google account.
So then you will have access to your own Google Drive. Everyone I think you get
Yes.
about 5 GB of storage there.
Yes.
So once you upload it to your Google Drive, then you can say open with Collab. So these are available for all accounts.
Okay.
You have
Okay.
access to
Okay.
your Collaborate and you can do that there.
Okay. 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 So no special interpreter or compiler is required.
Oh no, everything is installed. Everything is available. Even GPUs are available here. So if you go here and say change runtime type, you can select a GPU also if you want to use GPU for running your code.
Okay. Okay. Thank you.
Okay.
Thank you very much.
Okay. Thank you.
Sir, can you just tell brief about this logistic regression, sir?
I think you are on mute.
Oh yeah, I forgot. So for logistic regression, you will have, suppose you have two classes, a 0 class and a 1 class, and you want to learn a function such that you maximize your probability that your function is 0 or your probability that your function is 1. You want to maximize your probability. So here there is a special type of function called the logistic function or the sigmoid function. Or a logistic function. So one thing you should always take care is that logistic regression. So even though we say that it is a regression, it is actually used for classification.
Then why is the name regression, sir?
That is because you want to maximize your probability, right? So regression is, this term regression is used for when your output is a continuous
Yes.
value. So since we are trying to maximize your probability and probabilities are continuous values, so they say that it is a heuristic regression, but based on your probability, it is actually a classification. It is used for classification. So yeah, so they use this type of function called a sigmoid function. So it is denoted by sigma and given some, say, W transpose X, it is represented as 1 by 1 plus e to the power minus W transpose X. So this is a sigmoid function. So suppose instead of W transpose we have some other things, theta. So this function, it looks like this. So this is your theta, this is your y. So this function, so this is 1, it lies between 0 and 1. At 0 your value is 0.5 and else it either it gives yeah, it lies between 0 and 1. So what we want to do is, suppose we have some classifier, say whose parameter is given by, say, W. So if W transpose X is less than 0, so if it is less than 0, your functions will run in this point, right? So then your sigma value will be less than 0.5, right? Sigma of this W transpose X will be 0.5. If W transpose X is greater than or equal to 0, then your sigma value will be greater than equal to 0.5. So what it means is that if you have some classifier and your classification score is less than 0, then you say that your probability, your class belongs to class 0, because you get a probability of for class 0. If your this classifier gives a probability greater than 0.5, you say that your class belongs, your object belongs to class 1. So this is the basic way how this logistic regression works. Are there any doubts?
Can I ask a question on a decision tree?
Yeah, sure.
See, when you select a root node, how do you do it? One with the lowest entropy or one with the highest information gain? Are they at times contradictory or no?
So those are two different things. Actually, your information gain, you can write it in terms of your entropy. I think entropy or some function of your entropy. So what entropy does is it measures how uncertain your data is. Suppose you're at some node, suppose you have 15 examples of class positive class and say 5 negative class examples. So for positive class your ratio is 15/20, and for negative class your ratio is 5/20. So this is bit uncertain, right? Because given a point, it has this much probability of being positive, this much probability of being negative. So information gain, what it does is, it will at each node, it will try to split on that data point for which your entropy minimizes. So ideally we want all examples to belong to same class. So in that case, suppose we have some node and we have all the 20 examples belong to the same class. So in that case, your ratio is 20/20, which is 1. So we say that when in this case your entropy is 0. Entropy is 0. So that means there is no uncertainty. Given any point from this, we know for certain that it will belong to the positive class. But in this case, there is some uncertainty because we cannot clearly say what is the class that the point will belong to. So this information gain, it computes which according to the attribute that you are partitioning on, what is the reduction in entropy. You want to reduce your entropy because you want to reduce your uncertainties in the data. So information gain measures how much reduction it is happening, and the attribute which gives us a maximum reduction or which is said to have the maximum information gain. So that is the difference between entropy and information gain. Is it clear?
That information gain and entropy have more or less a reverse relationship.
Yes,
Though
you can
not
say.
exactly reverse, it won't be reciprocal, but it will be something qualitatively reverse.
Yes, your if
Lower the entropy, higher the information gain.
yes.
Okay, thank you. So in short, once again, to conclude, when you select a particular feature for a node, we should concentrate more on calculating the information gain and see that that information gain is the max for different features.
Yes. Which feature gives us the most information? Yeah.
Okay. Okay, is there any resource where we can find last year's assignments or previous year's assignments or previous year's exam papers on NPTEL?
I don't think so, because those are limited to the website, right? So I'm not sure if they somehow publish those. I'm not aware of that. You can mail the NPTEL team and ask for it, but I am not aware.
Okay. With linear regression, when you increase the size of the training data set, there is a possibility that there's a possibility that the training error will reduce. Is this the right statement?
Yeah. If this, I think this question is given in the assignment, and I will not be able to answer that.
Okay.
Sir, in Saturday class, sir said that bias and variance decomposition will be taken up if possible.
Okay. So yeah, I think it will be taken up in tomorrow's session.
Okay.
So I'm not prepared much for that.
Okay.
So basically, it says that the loss that you have, the test loss that you have. So in general, just in simple terms, it can be written as bias plus some variance square and some other term is there. So we don't care about this term. So we want this bias and variance to be controlled, because we want our model to have lower bias, but if we have too low bias, we'll have high variance. So there is a trade-off between this bias and variance. So I'm not prepared for this bias variance trade-off, so it may be taken up in tomorrow's course, or we can discuss it in the next session.
Okay, sir.
Why is it necessary to have a validation data set? I mean, you are dividing a training data set into training and validation and test. What happens if you don't do validation and just go to test? Anything, is it necessary?
Yeah. So suppose, so when
Sir,
we're
shall I
talking,
answer this question?
yeah, sure, go ahead.
Sir, what I feel is, see, it is like we have done a training and our model is ready. If there is no validation and suddenly it is given with the test sample, the error what we get will be too high. So that is a reason why before introducing it into like a real live data, we first divide the samples and into 70, 15 and 15. And we first, even that becomes an unseen data for the training model. And what they do is, it is not that we finish completely on the training example. When we are done with some 50% of the training sample, we undergo validation and we try to tune the parameters. And this process continues. Maybe we can do this iteration for 10 times on the training sample against validation. And then we can say that the number of errors is reduced. That is when we give this training, I mean, we apply the test data onto the model.
Okay, just to put it very, what we call procedurally, we have got a training data set. Okay, on that we calculated beta 0 and beta 1. Now we go to the validation data set. What do? We change this beta 0, beta 1?
So, yeah, one you can answer.
Yes, sir. Yes, we have to tune it.
But the validation data set, at least from the slides shown by Professor Sarkar, is of a much smaller size than the training data set. So, so there is a great chance that in the process of tuning, you are increasing your error, because that's why I asked that question earlier. With the increase in training data set, does the error reduce? Unless the validation data set is more than the training data set, then only I think it will be of use, isn't it?
No. So the validation dataset is not used for training. Only the training dataset is used for training. Validation dataset is just for looking or just for checking the performance of your model. So in the industry we have this production code, right? So sometimes we test our system on some local code that is available, and only then, if it satisfies all the tests, we move the code into production. So validation is like the local data that you have, and test data is like the production code that you have. We don't want your model to go out into the production without looking how it performs on the local data that you have. So it is like analogous to that, if it is clear.
Okay, yeah, I mean, it is clear intuitively. I mean, I understand. Only if I take it procedurally, you have got beta 0, beta 1 on a training data set which is, say, of n parameters. I mean, sorry, of n points. Okay. Then you have a validation data set which is only 0.1%, 10% of the training data set. Then what happens to this beta 0, beta 1? Is it really a good idea to tune this beta 0, beta 1 only on a data set which is to 1/10 of the training data set?
So no, when we talk about tuning, we're not talking about tuning these beta 0 and beta 1 parameters. These are the parameters that are learned by the model. When you talk about tuning, you talk about tuning these hyper parameters. So this alpha here is user defined, right?
Okay.
So that's, we want to see like which alpha will give us the minimum or best loss on the validation data set. So that is what we refer to as tuning. So these are learned by the models. We don't give these explicitly. These are not given us by the user. Only these hyperparameters are require training for this, and only based on the performance of the validation set, we want to see which set of parameters, or there may be more than some other hyperparameters. So which set of hyperparameters performs best? So that is why this validation test is.
Okay. But when the training data set is given, automatically B1, beta 0 and B1 will be calculated, isn't it?
Yes, based on
On the basis of which alpha?
on the basis of alpha that we give. Suppose we say that alpha is 0.1, it will learn some beta, not beta 1. Suppose we say alpha is something else, it will learn another, because we suppose it will stop here, it may stop here, we don't know. Based on different alpha, after some iteration, it will stop at some point.
Okay. And then then you go to the validation data set, which consists of, once again, nothing else but the points, new points.
A smaller set of points, yes.
And on that basis, you only change alpha.
Yes, if we check and see, so your validation set will give some validation loss. So suppose for some alpha we will get some loss. So here we are varying alpha. Suppose we get a loss here. Suppose for this value of alpha you get a loss here. With some, suppose 3 values of alpha, our losses are these. So we see that at this alpha your loss is minimum. We will use this alpha for tuning our model, and you use that model for the test set.
But can't that be done on training data set?
So no, because we want to evaluate our model based on how it performs on unseen data. So this validation data is not seen by it is not used for training. So what happens during training? It is looking at the training data, computing the loss based on the training data, and updating the parameters. So that is, the training data is a seen data. We want to see how it performs on unseen data. So this validation set is another set of unseen data that we extract from the training data. We do not use it for training.
Okay. Okay, ठीक है, थोड़ा समझ में आता है. Only confusion is, why, whether validation data should be a part of the training data set, or should the validation data be a part of the unseen data, that is the test data set.
So it is you can say that it is an unseen data. You just separate it from a training data generally, because it is available to you. You separate it from the training data and do not use it for training. You just use it for evaluating.
Yeah, I think the analogy of code and test server and the production server, it fits more, which that makes it a little more clear. Okay.
Sir, how the learning efficiency is calculated, sir? The model's learning efficiency.
Okay, so there can be different, like you will have different measures of efficiency, right? Like if you want to check in terms of time, which algorithm performs the best in the given amount of time, or which algorithm requires the least amount of time, or you may want to check which algorithm requires the least amount of memory. So it depends on what type of algorithm you are using. So suppose you are using this gradient descent, right? So this gradient descent you will require computing the loss for all the data points. So this requires a lot of memory. But if you are doing stochastic gradient descent, because you are using a data point at each round, you'll require less amount of memory in that case. So you can say that in terms of memory, this algorithm is more efficient. So it depends on what sort of efficiency metric that you are using.
Okay.
Okay, okay, go ahead. Okay, in most statistical software, like SPSS or SAS, okay, you give in linear regression you give a set of points which is what you call training data set, but they never ask for alpha. So where does alpha actually coming from the user point of view, from the hyperparameter?
So I have not used those software, so I cannot say. But when you're training, so I think there should be some. So this is called a learning rate. So there may be some parameter called learning rate, what that you want to use. There may be some slider or something like that. I have not used those software, so I cannot say for sure. But
okay, but
yeah.
you mean any linear regressions software will always ask for alpha.
Yes, because if you're trying to train it from scratch, if it has the provision that you can train it, so it will ask for some alpha, and it may ask for even other parameters, like if you want something polynomial or something like that, so it will ask for it.
Okay, yeah. Yeah,
but I've seen those software, so I cannot say for sure.
Okay,
So
let us take Microsoft Excel. They give you various choices. They give you either want a linear regression or you want a polynomial, what degree of polynomial, whether you want a logarithmic fit, etc. Suppose I choose linear regression and I give them training data set. That means they automatically draw a straight line. They never ask for alpha.
Oh, so how? Yeah, so this linear regression, it also has a closed form solution.
Okay.
So this closed form solution, what it does is it computes some matrix vector products, because suppose this is your data matrix and this is your test label vector. So it will compute some models W, and it requires some matrix multiplication, matrix inverse, that sort of thing. So if given a small amount of data, it will compute this model and then apply this model to the test set. And then this can be done deterministically. So this alpha and all these are, if you're doing gradient descent type of algorithm, these are iterative algorithms, then you require these sort of parameters to be given. But I think Excel uses this closed form solutions or algorithms, then they don't require these tunable parameters. That's why they don't ask for it.
Okay.
This is how I understand it. The actual.
I think you may be correct, because most of the standard software like SAS, which is industry standard, or SPSS, they also use, I think, a closed form solution. And probably some sophisticated versions of them may be asking for alpha.
Yes, maybe.
Okay. Thank you. Because this was the confusion, because I've been using this linear regression software, but nobody asked alpha anytime.
Okay.
So it will be fair to say that validation data is, you can say, unseen data as far as the training the model is concerned, because model is already trained.
Yes.
And you are only partially testing the model to tune using validation data.
Yes.
So it is like unseen data, but it is helping you to tune further.
Yeah, this is the unseen data, but yeah, test is different because it can be anything. So it is just a proxy for the test data set.
Yeah. So validation data has both the labels X and Y,
Yes.
but test data has only X, no Y.
Yeah, train data also has X and Y, but
test.
Test do not have Y.
And validation data will have X and Y both, as well as training data.
Yes.
Okay. Now things are getting clearer. At least, because many times we use all these things blindly, just push things into a software and get a linear regression, and you get the beta 0. So we don't go deep into it. That's why these questions.
Yeah. But yeah, those are nice conceptual questions.
Yeah.
Sir, can you tell something about this pruning decision trees?
So before going into putting we know this problem of overfitting, right? Because we don't want our model to overfit to the training examples. So suppose we have some data set X, and suppose it has 10 features. So that means at each step of our decision tree, it will try to split the data based on each of these features. So suppose this is a very deep tree, like at each step they perform a split such that when it goes to the leaf node, there is only one data per node. So only one data per node. So that means it is massively overfitting to the training data set, because it is like memorizing this data set. But if you give a test data, it will follow along this tree. But since these are overfitting, it will be mapped to some leaf node which does not perform as well, because it has memorized the training data, but it will not perform well on the test data. So what we don't want very deep trees. We don't want this sort of trees. We want some trees which have some less depth, because in that case we can control the degree of overfitting that we have. So then this concept of pruning comes. So what is pruning? Given some decision tree, we try to, so pruning is given decision tree, we reduce the height of or depth of the decision tree. So this prevents overfitting. So in the lectures, I think ma'am has discussed some techniques for pruning. So one of those techniques is like using the validation set. So suppose you are using a validation set, you try to remove the tree rooted at this point, and you measure the error. So what is the error given by this decision tree, and what is the error given by this decision tree minus this subtree. If the error is not much, then you can remove that tree. So that is a pruning technique that has been discussed. Another pruning technique that is there, like we were talking about information gain, right? Information gain. So after some depth, if the information gain is not much, so that is you are not getting any additional information, so you can stop the growing the decision tree at that point. And there are some other techniques also. I think some MDL or those techniques are there. So those techniques, so the basic idea is we don't want to memorize the data set. So yeah, so are these basic techniques clear? So there are both bit complicated techniques also. So this MDL can be seen in this sklearn library. They use MDL for, you can see the MDL for checking your complexity of your model. You want your model to not be very complex, but you want some complexity. So this pruning controls the level of complexity that you have.
Okay, sir.
So we have around 20 more fields to.
In the Professor Sarkar's lecture, she said she has made a statement that decision trees can be expressed as a Boolean function. Disjunction of a conjunction. Okay, what does this mean? This means that it can be conjunction means a union, right? Union of is A union B is conjunction, right?
A union B is yeah, conjunction. You say that.
So conjunction is a disjunction of conjunction means what? A union B intersection into brackets C union D. Is that the meaning?
Yes.
So how is go ahead.
So if you have this node and you are splitting into two parts, right? So either this will be a 0 or this will be a 1. So this is a Boolean function that gives us 0 or 1. So then you so again you will have a 0 and 1. So each step you will having a conjunction, and at this step you are having a disjunction. So this is a disjunction of so at each step you are having this conjunction and you are doing a good disjunction of these steps.
So which is the conjunction? Conjunction is at a node, that is a conjunction?
So this or is your
conjunction.
Or is your disjunction. Wait a minute.
No. And is or is a conjunction. This or that. That means it's a union.
And is a conjunction. Or is a disjunction.
Or is a conjunction. See, if you have draw a Venn diagram, you have A and you have B, and say they are intersecting. So A union B means A or B. Yes. So that is a conjunction. A intersection B is A and B. That is a disjunction.
Yeah, sure. So yeah, so that is what Professor Sarkar meant. So at each step you are having these conjunctions, and then you are combining it with your disjunction.
Okay, and she also says that that decisions tree represents a non-linear function. That means if it is sometimes I get confused. This is a little bit of not a practical question but a philosophical question. If it is a non-linear function, how are we using it how can it be used in linear regression? Okay, so kahi discontinuity hoga, isn't it?
So mathematically speaking, non-linear functions are of this form. If you have some ax plus by, you can write it as in this way. So functions of this sort are called to be linear functions.
Okay.
So when we say about the decision trees, we cannot write it in this way. So that's why it is referred to as a non-linear function. Or you can say that a linear function. So suppose you have some space here, it will say map this space to some other space. But a non-linear function will say if you have some space here, it will go to some other space which is not linear. So that is a theoretical definition of this linearity and non-linearity.
Okay. Okay, and even in a decision tree, what she's saying is that I can understand this. When do we stop further decision tree is when all the examples have the same value for the attribute. Okay, that means it is homogeneous. Okay, examples are very too few. That means there are too few examples, so we don't. It will not give you any practical gain if you move further. And third one she's saying is the examples of attributes are exhausted. Are the two, what are the difference between the two? Any difference in these last two sentences?
So when we say that there are not enough examples, so suppose we have 2 points here, right? 2
Yes.
plus and or say 1 plus and 1 minus. Your ratio will be 0.5 and 0.5.
Okay.
Right? So it does not. So you can make it. We can have one more set of division, and then we can set a proportion to be 1. So suppose you have say 100 features and only 100 features had some nodes still left, and your examples is say 10. So based on these 100 features, you cannot have a good estimate of how to divide this, right?
Okay, yes.
So I think that is what is meant by that statement, when we have not enough examples for a given set of features.
Okay, that means examples are too few, and examples of attributes are exhausted. Matlab, all examples are exhausted, and yet we have not found anything homogeneous. But since there are no examples, we can't go further.
So yeah, so suppose we have this decision tree, and we are going in this direction. So we'll only have one branch. So the other branch, there are no data of the other branch.
Yeah. Okay. Are there any resources outside, say, NPTEL, where we can solve whether such examples for solving are available? I don't know whether NPTEL will provide. So I mean, because we have gone through Tom Mitchell's book, it is pretty exhaustive.
Yeah.
Okay, and the exercises there are not are of a completely different type. So something
theoretical, yeah.
Pardon?
Those are a bit theoretical.
A bit theoretical, quite theoretical of a different type. So are there resources available where maybe some other books where such examples are given where we can solve? Because only just a few, one assignment concepts don't sink as deep as they should.
So you can look at these online courses, not online courses. I mean, most IITs, they publish this lecture notes and problem statements. I think from IIT Kanpur, IIT Delhi, or even if you go for internal, I think Stanford, MIT, they publish their assignments online. So I cannot give, I am not sure about the course codes, but if you just search for it, MIT Open Courseware or something like that, you will get some assignments there. So you can work on those.
Okay. Okay, only 12 minutes left. No questions. I don't have any further questions. Thank you very, very much for answering all questions.
Thank you. It was great interacting with you. So if there are no more questions, I think we can end this session.
Yes.
So thank you all for attending.
Thank you. Thanks a lot. Thank you very
Thank
much.
you.
Thank you.
Thank you.